Okay, so take a look around you. I mean, right now. Chances are you're not far from some concrete. It's literally the foundation of our modern world, the most used building material on the entire planet. But have you ever really stopped to think about how it works? I mean, it starts as this wet, gray sludge, and it turns into, well, artificial rock. It's an incredible transformation, and it all comes down to a secret chemical story that's happening deep inside.
So what's the deal? How does the soupy mix of cement, water, and sand turn into something strong enough to hold up a skyscraper? Here's a hint. It's not just drying out like a mud puddle on a hot day. Oh no, the real answer is so much more fascinating than that.
It's all about chemistry, a really powerful chemical reaction. The moment cement and water mix, they kick off this process that completely rebuilds their molecules into a new, super strong interlocking structure. And here's the kicker. Like any good powerful reaction, it gives off a signature calling card, heat. And understanding that heat, well, that's the key to unlocking everything.
All right, so if heat is the secret code, how do we crack it? How do we listen in on that chemical conversation? Well, scientists use a technique called calorimetry. This is our backstage pass, letting us peek inside the concrete as it hardens and read the story of its transformation second by second. Honestly, the best way to think about it is like a doctor's stethoscope, but for concrete. We're not just checking for a fever, we're listening to the rhythm, the pace, the intensity of its chemical heartbeat as it comes to life. And that heartbeat tells us everything about its health and its future strength.
And that chemical heartbeat? It's got a name. Hydration. Now, don't get this confused with just being wet. This is a full-on chemical bonding process. We're talking about water molecules literally joining forces with cement particles to build something new. This hydration process is the engine that drives the whole thing, and it's what releases all that heat we're measuring.
Right, so when it comes to actually listening in, scientists have basically got two main types of these stethoscopes, and they use them for very different jobs.
So on one hand, you have isothermal calorimetry. Think of this as the super precise lab coat kind of tool. It takes a tiny sample and measures the exact flow of heat while keeping the temperature perfectly constant. On the other hand, you've got semi-adiabatic calorimetry. This is more of your real-world, boots-on-the-ground tool. You take a much bigger sample, you insulate it, and you just see how hot it gets. So one is for deep R&D, and the other is for practical quality control out in the field.
So we've measured the heat. What now? Well, this is where it gets really cool. All that data creates this unique curve, what scientists call a heat signature. It's basically a fingerprint that's unique to that specific concrete mix. And if you know how to read that fingerprint, you can predict exactly how it's going to behave.
And this signature, it tells a story in 4 distinct chapters. First, right when you mix it, there's a quick burst of activity. Then, things get quiet. That's the induction period, and it is absolutely crucial. It's the workable window when crews can pour and shape the concrete. After that, bam! The reaction kicks into high gear, the accelerating period, and that's where most of the strength gets built. Finally, things slowly wind down as the concrete matures.
And here's the most important part, the exact shape of that curve, how high the peaks are, how long each phase lasts, none of it is random. For an engineer, it's a perfect roadmap. It tells them exactly how fast that concrete will set and ultimately how strong it's going to be.
And yeah, this is so much more than just an abstract science project. Understanding this heat signature is literally what allows us to build the modern world. We're translating data from a tiny sample in a lab directly into the safety and durability of massive structures.
This right here is the ultimate payoff. It's a total game changer. By measuring the heat for just a few hours or a couple of days, engineers can predict with incredible accuracy the strength that same concrete will have weeks or months later. It's basically like looking into the future, and that lets us build faster and safer than ever before.
But you know, it's not always so simple. Modern concrete is rarely just cement, water, and sand. We add all sorts of special chemicals called admixtures to make it set faster or slower or flow better. These additives can be incredibly helpful, or, if you get it wrong, they can cause a complete disaster.
Okay, take a look at this graph. This is what a catastrophe looks like in data form. See that flat black line at the bottom? Compared to the healthy curves, it shows almost no heat, which means almost no reaction. This is what happens when you use the wrong additive. It causes a flash set. The concrete gets hard instantly, but it has zero actual strength. It's totally useless.
Calorimetry lets us catch this disaster in the lab before it ever happens on a construction site. But it also shows us the path to success. Each of those colored lines you see here represents a concrete mix with a different additive. You can literally see how some delay that main reaction while others kick it into high gear. This is how engineers can test dozens of combinations to design the perfect recipe for any job, whether they need it to set slowly in the desert heat or super fast in the freezing cold. And this level of control isn't just a nice-to-have. It's absolutely critical for massive projects. I mean, think about a giant structure like the Hoover Dam. The heat from all that hydration could build up so much that it would cause the concrete to crack itself apart from its own stress. By using calorimetry to precisely control that reaction, engineers can ensure these amazing structures will last for centuries.
So, the big takeaway here is pretty simple, but it's also profound. By learning to listen to the quiet and visible release of heat from this everyday material, we gain the power to predict its future, control its performance, and build structures that are stronger, safer, and more durable than ever before.
It really makes you wonder, doesn't it? This is just one material. What other secrets are hiding in all the other materials around us, just waiting to be unlocked if we learn how to read their hidden chemical stories? What can we build next, once we learn to listen to them all?